Okay, so in this video we'll talk about improper integrals. And the reason why we call these integrals improper is because the way we've defined integrals so far, which is using your Riemann sum definition, right, of dividing your interval into n equal with subintervals, and then taking the limit as n goes to infinity to get the exact area. This is not going to work for these integrals that we'll be seeing in this section. And well, one reason why this won't work is, well, sometimes you're interested in finding this area of an infinite region, right? So if you look at this integral here, oh, that's a typo here. That should be the integral from 1 to infinity, right? So that we know corresponds to this infinite area under the curve of y equals 1 over x squared. However, we can't really do a Riemann sum here, right? Because your upper limit b is infinity. And so we can't divide b minus a by n and get, and do all that stuff. So we can't do that here. So what are we supposed to do in order to compute this limit? Idea, oh, I mean compute this integral, but I pretty much gave away what we're going to do in this case. The idea is to cut off this infinite region somewhere first. Let's say at some point t. So we can say, well, let's compute the integral from 1 to t of 1 over x squared dx first, right? Where t is some number larger than 1. Okay, and so in this case, well, that's easy. That's minus 1 over x evaluated from 1 to t. And therefore, this is minus 1 over t plus 1. And that's a general formula here, right? I can plug in t equals 3, for instance. And I'm going to get negative 1/3 plus 1 equals 2/3. And that gives me, well, exactly the area here. I can plug in t equals 4. And I get the area here all the way to 4. And so another idea is maybe we can take the limit as t goes to infinity. Right? I mean, we have a general formula now. If I plug in t equals 1,000,000 here, it's going to give me the area under the curve from 1 to 1,000,000. And, well, okay, let's do that. Limit as t goes to infinity of whatever this integral was. Right? And this gives me minus 1 over t plus 1. And as t goes to infinity, the first term just disappears, goes to 0. And I simply get the number 1. And so it turns out that this is exactly how we're going to define this integral right here. If you have infinity as the upper bound, you're just going to have to cut off your area at some point, t, find the general formula for the area of that region up until t, and let t go to infinity. Right? So even without using our, typical Riemann sum definition for the whole interval from 1 to infinity, we're still able to do something clever here, right? Using limits in order to take the integral or to evaluate this infinite area. And this will not always work, actually. And I'll give you an example here. Again, that's a typo here. It should start at 1. And I just changed the function a little bit, right? We start at 1, go to infinity, but the function is 1 over x. And 1 over x, as you can see from the graph here, is larger than 1 over x squared, right? If it was smaller, then a good guess would be that it also has a limit or a value, right? Because this infinite area is equal to 1. But now we have something larger, so we don't know anything about this yet. So let's try the same idea. Let's compute the integral from 1 to t of 1 over x dx. And that's equal to ln x evaluated at 1 at t And that's ln t minus ln 1, which is 0. And so when we try to take the limit here, what happens? Well, the limit as t goes to infinity, 1 to t of 1 over x dx, is the limit as t goes to infinity of ln t. And, well, this doesn't exist, right? This actually goes to infinity. And what this tells me is that this area under the curve here of 1 over x is unbounded, right? That's infinity right there. It's not equal to a finite value. And so we do actually have a name to describe the behavior here of the previous integral that did have a limit, and this integral that does not have a limit as t goes to infinity. And what these integrals are called are either convergent if it has a limit, right, if the limit exists, or divergent if it's not. Right? So convergent means when you evaluate the area, it's actually a finite area. Divergent means it's infinite. And what we basically did in the previous two examples was, this first bullet point here, which says, if you cut off your infinite area at t, right, and put t as the upper limit, and if the limit of that region as t goes to infinity exists, then we will say that this improper integral exists or is convergent. And in fact, we can do the same thing for integrals where you have minus infinity to some number. And in that case, it's basically the same idea. You're going to be cutting it off at some value t and letting t go to minus infinity to get the infinite area. All right? And again, if the limit exists, then it's convergent. Otherwise, it's divergent. And yeah, so that's basically it. And here's an example where you do have minus infinity for the lower limit. And so let's just do this example here. We know from the previous slide that what we want to do is to look at, well, whatever the value of this limit is. Limit as t goes to minus infinity, minus t to minus 5, x e to the x dx. Okay, and the first thing you want to do here is to evaluate the integral. I'll do this separately here. X e to the x dx, while using integration by parts, you're going to see that this is x e to the x minus e to the x plus c. So what this means for us is this is the limit as t goes to infinity of, well, this function, but you plug in negative 5, and then minus what you get when you plug in t, right? So t e raised to t plus e raised to t. Okay, and I'll just box this off here. This is what we use to evaluate the integral. And now we've evaluated it. And this is now, this whole thing is the area under the curve of y equals x e to the x between x equals t and x equals 5. Right? And now what we're going to do is we take the limit as t goes to infinity. And what happens? Sorry, this should be minus infinity. Well, these are just constants at the beginning, so we don't really care about that, right? They're just going to be there. So what I'm going to do is I'm going to take the limit as t goes to minus infinity of these other terms. E to the t, that just goes to 0. Right? Y equals 0 is a horizontal asymptote of e to the t. Now how about the limit as t goes to minus infinity of t e raised to t? Well, that's actually an indeterminate form here. Right? This is minus infinity times 0. So using ideas from differential calculus, I'm going to rewrite this as t divided by e raised to minus t using a law of exponents. And the reason why I did that is because now it's in the form minus infinity over infinity. And so we can use L'Hopital's rule, take the derivatives of the numerator and denominator. This is now 1 divided by minus e to the minus t. And finally, I can just write this as minus e raised to t. And that's also 0 when you take the limit. Therefore, combining everything that we did here, integral from minus infinity to minus 5, x e to the x dx, well, is convergent because it has a limit and is equal to minus 5 e to the minus 5 minus e to the minus 5 and then minus 0 plus 0. So that's the final answer. Now, lastly, I just want to say you have to be careful if you have an integral that has both infinity and minus infinity in the same integral. Because sometimes you may be tempted to do something like this, where you cut off your integral at symmetric values of t. So you do limit as t goes to infinity of minus t to t of f of x dx. And that's not actually going to work here, right? And I'll give you an example. What if you use the function x? So if you did this and took the limit as t goes to infinity, right, for both sides, then what you're going to get here is, well, that's 1/2 x squared evaluated minus t and t. And, well, that's 1/2 t squared minus 1/2 t squared. That's actually just a 0. So this limit is 0. Right? And that makes sense for the graph of y equals x, because if I cut it off at symmetric x coordinates, the areas here will just cancel each other out. That's why that's always a 0. But it doesn't make sense to say the infinite areas are going to be 0. That's kind of like saying infinity minus infinity is 0, right? Which is doesn't really make sense, right? That's another indeterminate form, if you remember. And so what you'd have to do if you have an integral from minus infinity to plus infinity is you need to break it up somewhere, anywhere, and compute two separate improper integrals. Right, so break it off here and let t goes to infinity, and maybe cut it off here and have another tier, let's say s, and let s go to minus infinity, and compute these areas separately.